Hello everyone. In this video we will talk about the interaction between the structure and the foundation. As you know, there are three different interactions in STA. The first is the separate solution for the structure and the foundation, and the second is the combined solution for the structure and the foundation, but we have rotational freedom at the foundation. In the third case, both rotations and settlements have been released in the combined solution of the structure and foundation. So how does this happen? We model our soil using springs when constructing the stiffness matrix. Springs also have freedoms. In this way, in the second and third options, the foundation matrix is also included in the global stiffness matrix. This is how the solution is carried out. So, in which situations do we need to use these, and what changes for us? In the first case, in the separate solution of the structure and foundation, if our soil is solid, meaning it is rocky, or if we have a basement, we can use the first option. With a rigid basement, we can choose the second option as a general solution method for soils that are neither swamp or rocky. The third option is used only in swamp soils. The reason for this is the need to consider settlements. In other words, if we want to reach a realistic solution, we can choose these according to our type of soil. So, what will change in our structure? Now we will compare these. We will solve our sample 7-story model. First, with the first option, then with the second option, and finally with the third option. We will look at what changes will occur in our period and shear wall moment. Now let's choose our finite element analysis, FEA, option for the structure. Let's select our first option. Let's make our general arrangements. We are conducting our checks. Our first option is selected. We will see what changes will occur in our walls and our period. Let's save this as base 1 and start the analysis. Yes, our analysis is complete. The period of our structure is approximately 0.54 seconds. Now, let's examine our walls. The design moment of our wall is approximately 3,500 ton-meter. We can say around 3,500. Now, let's look at our second wall, which is also approximately about the same. This was the first option, so it was assumed that we did not have a foundation. The bottoms of the columns and walls were considered very rigid. The solution was made in this way. Now, let's choose our second option. We are not changing anything. We are just introducing interaction. We said OK. We renamed it to Complete 2 and are starting our analysis. Yes, our analysis is complete. Since our foundation has freedom of rotation, we expect an increase in our period and a decrease in our moments at the base of the shear wall. So, what is the reason for the increase in our period? Since our structure was modeled together, it exhibited a more continuous behavior at the foundation. In other words, since our ground, modeled with springs and dampers, is open to rotational freedom, it exhibited a more continuous behavior. which is why our period became 0.65 seconds. Let's note that. Now let's check our shear walls. Yes. There is a very high degree of reduction in our shear walls, almost a halving. Our moment, which was 3,500, has dropped to around 1,700. This is due to the structure being subjected to lower moments because of its ductile behavior. Now let's try our third option. The third option is almost similar to the second option. We are marking our third option. We recorded it. Yes, we are currently and thoroughly analyzing it in great detail. Yes, our analysis is complete. Our structure's period has increased from 0.65 to 0.72 seconds, which is again a behavior we expected. One of the reasons for this is related to the number of ground floors, which will vary according to your project. Our structure has behaved even more ductile due to the ground. Now let's examine our shear wall. Due to the increasing effects, it has taken a value not around 3,500, nor around 1,700, but somewhere in between. Because both rotations and settlements have been taken into account. This is the reason. Yes, our analysis is complete. As we discussed earlier, our structure's periods have gradually increased, and as a result, our reinforcements have changed, the moments of the shear wall have changed, and the reinforcements in the beams have changed. Many things have changed in our structure. Now, let's move on to our options in the foundation design. These are advanced options. Let's discuss this now. We are opening analysis option for raft foundation. Here. I will start informing you now. Yes, now let's elaborate. Detail on our basic options. Here we have a unit width for the finite element section, and we have our water level. Additionally, we have three options for Winkler springs. So what do these mean? The first option is where there is nothing next to our structure, and we only have Winkler springs symmetrically beneath it. I can explain this as follows. Essentially, here is our structure. This is our foundation. Here we have our Winkler springs, these objects. We drew our springs. So what does the first option mean? It means that our ground comes in this way, and there is nothing around it at all. This is indeed just simply put as being the very first option available to us. In other words, there is no building or road on this side whatsoever. We have a building right in the middle of an empty lot, and we can use this there. The second option involves an area here. We have a foundation area here, and we have a building area. Additional springs are also assigned to these areas. There are also springs here. Our structure is calculated in this way. In other words, the springs are modeled and taken into account by considering the conditions corresponding to the settlements of the ground. Here we can also choose the area we will consider. So in which situations should we use this? if there is a building around our structure, there is a road, or if there is a situation that could affect the rigidity of our very tall building, we can specify the area and adjust the number of stories accordingly. As you can see in the photo, if it is higher than 5 meters, you do not need to take it into account. However, if it is less than 5 meters, we definitely need to consider this interaction. So how will we take this interaction into account? You will see that shortly. In the third option, the Pasternak method, springs are modeled with cross springs. As you can clearly see here, outside of these springs, we have our Winkler springs from the first option in the Pasternak model. These springs interact with each other, meaning that the rigidity outside significantly affects the rigidity inside. Calculations are meticulously performed as a complete network structure. The ratio here is directly related to the angle between these springs. Of course, these require advanced knowledge. If we have no knowledge about the subject, we should not use it. Now, let's call our foundation. We called our foundation. First, let's select our first option, and we will call our foundation. Called our foundation, divided it into finite elements, saved it, and are now analyzing it. And we analyzed it. Our maximum ground stress came out to be 13 tons. Now, let's select our second option. We selected our second option and called our foundation. The areas you see outside and be opened and closed. Right now they are passive. In which situations should we make this passive? In the modeled scenario, we have a structure here. There is also a relatively tall building that significantly affects this structure. Therefore, prevent the two from affecting each other. Since there is no ground here, we should close this area, meaning we need to make this part passive. This option is used in this way. Now I am recording. I am analyzing. Yes, our analysis is complete. As you can see, our stress lines have completely changed, and our maximum stress has decreased from 13 to 12. Now let's try our third option. Our third option is Pasternak. We select Pasternak. Call our slab. Divide it into meshes. Prepare our stiffness matrix. Save it and analyze it. As you can see, this time there was a change in stress at the edges as well, and the stresses in these areas also changed. In this case, following the stress lines would be the most accurate solution for you. The maximum stress we expect is the stress beneath the walls. We have had a stress around 12 again. So, what is fundamentally important? What is fundamentally important is the reinforcement. When we choose a 16 millimeters reinforcement and set our reinforcement spacing to 20 centimeters, it does not suffice. It also does not suffice when we set it to 15 centimeters. In this case, it is necessary to increase the diameter of the reinforcement. The area shown here and The program is the required amount of reinforcement. The area shown here is the reinforcement area we have selected. The program adds additional reinforcements and structural elements based on the reinforcement area we carefully selected, allowing it to effectively reach the tensile reinforcement area of a minimum of 0.2%. This way, we meticulously perform the reinforcement and subsequently obtain our detailed drawing. The drawing only shows the additional elements. While the primary structural reinforcements are clearly represented in the section as shown, you can easily see the precise locations of the additional reinforcements in this way. There is also a comprehensive punching calculation in this section, and we can thoroughly view the calculations from the Printer tab. Everything is satisfactory, and there are absolutely no issues. That's all I have to explain fundamentally and in detail. Thank you for listening to me. I wish everyone a good day.